In the previous lesson, we derived the nonlinear state equations for a magnetic suspension system. The model was x dot equals f of x comma u, where f contains terms like I squared over x squared. But all the powerful tools we have learned, transfer functions, Bode plots, root locus, they only work for linear time invariant systems. So how do we bridge the gap? The answer is linearization. We approximate the nonlinear model as an LTI system near a chosen operating point. This technique is called set-point linearization. The first step is finding an equilibrium point, also called an operating point. An equilibrium is a state where the system can remain at rest indefinitely. Mathematically, this means the state derivatives are all zero. So we set x dot equal to 0 and solve f of x0, u0 equals 0. Here, x0 is the equilibrium state and u0 is the constant input that maintains it. For our magnetic suspension, equilibrium means the sphere hovers at a fixed position with constant current and zero velocity. Let us find the equilibrium for the magnetic suspension. Setting x dot equal to 0, x20 equals 0 since velocity must be 0. From the force balance, G equals c times x30 squared divided by m times x10 squared. This gives us the relationship between equilibrium position and current. We choose a desired hover position x10, then calculate the required current x30 equals the square root of mg x10 squared over c. Finally, the equilibrium voltage is u0 equals r times x30. Now we linearize around the equilibrium. Define small perturbations. Delta x equals x minus x0 and delta u equals u minus u0. Using a first-order Taylor expansion, f of x0 plus delta x comma u0 plus delta u is approximately f of x0 comma u0 plus the partial derivative of f with respect to x times delta x plus the partial derivative of f with respect to u times delta u. Since f of x0, u0 equals 0 at equilibrium, we get delta x dot approximately equals a times delta x plus b times delta u. The matrix A is the Jacobian of f with respect to x evaluated at the equilibrium point. Similarly, B is the Jacobian of f with respect to u at equilibrium. Let us compute the Jacobian matrices for the magnetic suspension. The state equations are f1 equals x2, f2 equals g minus c over m times x3 squared over x1 squared, and f3 equals 1 over L times u minus r x3. For matrix A, we take partial derivatives with respect to each state. The partial of f2 with respect to x1 is 2c over m times x3 squared over x1 cubed. The partial of f2 with respect to x3 is negative 2c over m times x3 over x1 squared. The partial of f3 with respect to x3 is negative r over L. For matrix B, the only non-zero entry is the partial of f3 with respect to u, which is 1 over L. C equals 1, 0, 0 since the output is x1, and D equals 0. Here is the complete linearized model. The deviation state equation is delta x dot equals a times delta x plus b times delta u, and the output equation is delta y equals c times delta x. This is now a standard LTI system in deviation variables. We can compute its transfer function, analyze stability with eigenvalues of A, design controllers using root locus or frequency response methods. Remember, delta x and delta u represent small deviations from the operating point. The linearization is only valid near equilibrium. Think of it geometrically. The magnetic force is ci squared over x squared, a nonlinear curve. At the equilibrium point, we draw a tangent line. This tangent is our linear approximation. Near the equilibrium, the tangent closely matches the curve, so the linear model is accurate. But as we move far from equilibrium, the tangent diverges from the actual curve. This is why linearized models have a limited range of validity. The approximation works best for small perturbations around the operating point. Compare the nonlinear and linearized responses. For a small perturbation from equilibrium, the two responses are nearly identical. The linearized model accurately predicts the behavior. But for a large disturbance, the linearized model diverges significantly from the actual nonlinear response. The linear model might predict the sphere returns to equilibrium, while the nonlinear model shows it falls away. This highlights why linearization is a local approximation, valid only near the operating point. Let us summarize the set-point linearization procedure. Step 1. Find the equilibrium by solving f of x0, u0 equals 0. Step 2. Compute the Jacobian matrices A and B by taking partial derivatives and evaluating at the equilibrium. Step 3. Write the linearized model in deviation variables delta x dot equals a delta x plus b delta u. The result is an LTI system that approximates the nonlinear behavior near the operating point. This completes Lecture 3 on state space models. We started with linear state space representation, converted between state space and transfer functions, modeled nonlinear systems, and now we have learned to linearize them. These tools form the foundation for modern control system design.